In number 9, we are required to differentiate this function. So the first thing that we can do is to apply exponential rule to rewrite it such that we can be able to differentiate it comfortably. So if you apply exponential rule, what we shall end up with here is this function will be written in this form. So y will be equal to e to power ln of x to power x, because you know that e to power ln x to power x is the same as y is equals to, it's the same as y is equal to x to power x by exponential rule, and I talked about that previously. So but we can rewrite this as using laws of logarithms. X can be brought in front, so this would be e to power x ln x, and then when we differentiate, if we choose to differentiate this function, which you're going to do, we shall have to apply chain rule, because here we have a function inside another function. So basically dy over dx will be equal to the derivative of the inside part, which is that, I'll just write it as d over dx of x ln x, which is the derivative of the inside multiplied by the derivative of the outside. Now outside is just e to power u, so it will just remain the same, e to power u, and u happens to be x ln x. So now our interest is here. Okay, this is where our interest is. So we can go ahead and say, but the derivative of x ln x will be equal to, and this is why we apply product rule, because it's a product of two functions. So x multiplied by the derivative of ln x plus ln x multiplied by the derivative of x, and this will be equal to x multiplied by 1 over x plus ln x, and that is just the same as 1 plus ln x. So we can now be able to rewrite the original derivative uh, function, derivative of the original function in terms of the results that we have. So basically dy over dx will be equal to the derivative of x ln x, which is 1 plus ln x multiplied by e to the power of x ln x, and that will be the final solution. And by the way, we can even simplify this further in terms of what we had originally. So this can be written as, because we know this is the same as this, which is the same as that, so we can write this as x to power x multiplied by 1 plus ln x. Okay, and that's basically probably the simplest version of the solution. Um, this is x to power x. Okay, so we can be able to apply the same method um, in, well, not necessarily in this question. Um, so anyway, we are required here to find the equation of the tangent to the curve at x equals to 0 and the equation of the normal. So we have this function here. So let's start with part A. We have y is equal to e to power x. So Here, what we can do is we can use chain rule. So let u be equal to e to power x, and that will imply that y will be equal to e to power u, if that's u. So du over dx will be equal to e to power x, and dy over du will just be e to power u. So if we put these two results together, dy over dx will be equal to dy over du multiplied by du over dx, and that will be equal to e to power u multiplied by e to power x, and this is the same as e to power u, which is e to power x plus e to power x, and this simplifies to e to the power of e to power x plus x. So this is dy over dx. So we have the um, this function gives us the gradient of this curve at any point. So we can use this function here to find the gradient of the curve at x is equals to 0. So at x is equals to 0, the gradient of the tangent um, will be equal to, if you plug 0 in place of x here, so uh, that will just be 0 and that will be 1. So this will be e to power 1, which is just e. And to find the equation of the tangent, we need the corresponding y coordinate at x equals to 0. So at x is equals to 0, y will be equal to, we substitute in the original function, e to power 0, which is just e to power 1, which is e. And then at this point, we can apply the equation y minus y1 is equals to m into x minus x1. So basically, here we know y1 is e, x1 is 0, and the gradient is e. So that means that y minus e will be equal to the gradient, which is e into x minus 0, and therefore y will be equal to e to power x. Y will be equal to e multiplied by x plus e, and that will be the equation of the tangent. So for part B, we need to find the equation of the normal at the same point. So what we need is the gradient of the normal. So at x is equals to 0, the gradient of the normal will be equal to the negative reciprocal of the gradient of the tangent, which is negative 1 over e. And then we plug this into the point slope formula. So we shall have y minus e will be equal to negative 1 over e into x minus 0. And therefore, our equation will be y is equals to negative 1 over ex plus e. And that will be the equation of the normal at x is equals to 0. Right. Number 11, we are required to differentiate this function with respect to x. Now, what we can do is we need to prepare it before we differentiate. And probably the best way is to take the natural logarithm of both sides. So ln of x to power y will be equal to ln of e to power x. And we are hoping that we'll end up with a simpler function that we can work with. So by laws of logarithms, this will just be equal to y ln x, and this will just be equal to x ln e, which is just x. So we have y ln x will be equal to x. Now, if you divide both sides by ln x, you'll have y is equals to x over ln x, which is a much easier function to work with, especially because we know that this is a quotient of two functions, and therefore we can be able to apply quotient rule. So basically, to apply quotient rule here, we have dy over dx will be equal to ln x multiplied by the derivative of x minus x multiplied by the derivative of ln x over x squared, and this will be equal to ln x multiplied by 1 minus x multiplied by 1 over x squared. So the resulting expression will be ln x minus 1 over x squared, and that will be the derivative of that function. Part B, we have this function. Now here, similarly to what we just did previously, we can apply exponential rule to rewrite it so that we can be able to differentiate this easily. So if you apply exponential rule to rewrite this function, you'll have y is equals to e to the power of ln x to power 2x, which can be written as e to power 2x ln x. And now, once you write it in that form, you can use chain rule to be able to differentiate the resulting function. So dy over dx will be equal to the derivative of the power of the inside function, which happens to be 2x ln x multiplied by e to power u, which is just e to power 2x ln x. Okay, so now what we need to do is to find this derivative here by product rule. So by product rule, this will be equal to 2x multiplied by the derivative of ln x plus ln x multiplied by the derivative of 2x, and this will be equal to 2x multiplied by 1 over x plus ln x multiplied by 2, which will be equal to 2 plus 2 ln x. Okay, so which implies that the original derivative will be equal to 2 plus 2 ln x multiplied by e to the power of 2x ln x. But we know that this is the same as that, which is the same as that, which is the same as x to power 2x. So this will just be equal to x to power 2x multiplied by 2 plus 2 ln of x. That will be the required solution.